All right, so we're going to take a look at an example of a particular Bode plot that's probably a little bit more challenging. Um, so let's say we have this guy here, h of s equal to 10 times s plus 5 over s times s over 100 plus 1, like that. Okay. Now, I had posted online, I told you guys this a while ago, this sort of rules for hand sketching Bode plots. And I said, this is my general form right here. All right, I want my transfer function in this form. Now, one of the things that I have in there is this s plus minus n. If I have a polar 0 at the origin, meaning that I have this term right here, this s plus minus n, then it's a little bit more challenging to make the Bode plot. And in this particular case, I have this going on here, right? Basically, I have a pole sitting at the origin. And so when I have that, I go to my step 6 right here. So if I have a polar 0 at the origin, I have to follow this process instead of the first 5 steps. Okay? All right. First thing I'm going to do, though, is I do want to get this guy in the right form. Okay? So if I get him in the right form, that means I want to factor out that 5 on top. So I have 10 times 5 over s over 5 plus 1 over s times s over 100. Okay. Now notice, compare that to this form over here, right? You look at this guy. Now I have everything with a tau s, right, plus 1. And I can see that my tau z is equal to, looks like 1/5. And my tau p equals 1/100th. Okay. All right. So from that, let's simplify that and just say I've got 50 times s over 5 plus 1 times s over 100 plus 1, like that. Okay. Now, let's follow those various steps that I outlined there. So my breakpoints. Okay. So mark breakpoints. Okay. Well, what are my breakpoints here? My breakpoints appear to be omega equal to 5 or 1 over tau z and omega equal to 100 or 1 over tau p. Okay, so this is a 0. This is a pole. Okay, so what I should begin to do probably is to draft up for myself what my axes are going to look like. So my y-axis is 20 log base 10 of the magnitude of h of s. And then my x-axis is log 10 of omega, like that. Okay. Now, you remember the way we sort of mark up this axis. This is kind of the important part to remember. The way I always do this, I say, well, for different values of omega, and then log 10 of omega, we have, so if omega was equal to 1, the log of that is 0. If omega is 10, the log of that is 1. If omega is 10 squared or 100, the log of that is 2. If I had 0.1, this would be negative 1. If I had omega equal to 0, it would be all the way back at negative infinity. Okay, so let's start to mark these axes up for me. All right, so if I mark these axes, I know that the origin here is 1 radian per second. The mark that would be 1. So what I'm going to do is the logarithm I'm going to write on the bottom, right? And then I'm going to write down up top the corresponding omega value. So 0, 1, 2, 3, 4, 5. So down here, these are the log values. And up top are the actual frequency values that go with that. Okay. All right, now I did that for a reason, right? A couple of breakpoints that I see here, all right? I actually left one out. I see pretty clearly that I've got one at 5 and one at 100, all right? But I also have one at omega equal to 0, and this is a pole, okay? Now, omega equal to 0, if we look at this guy, is all the way back at negative infinity, okay? So let me keep going on this to see if we can figure out how to accommodate that. So here's negative 1, which is 0.1. Here is negative 2, which would be 10 to the minus 2. Here's negative 3, which is 10 to the minus 3, all the way back like that. And then I'm going to mark off my dB values. So here's 20, 40, negative 20, negative 40, negative 60, like so. Okay? All right. So the breakpoints, so omega equal to 0 is all the way back here. Omega equal to 0 is way back there. Now, omega equal to 5, if I want to figure out where that is on a log scale, the thing I have to ask myself is, what is the log base 10 of 5? If you compute that, what you end up getting is that this is about 0.699. So that means that on the log scale, 5 radians per second sits somewhere between 0 and 1. Sits at about 0.7. So that puts it right about here. Okay? So this is my first is one of my breakpoints. Omega equal to 100, if I take the log of 100, that's 2, so that's a breakpoint here. Okay? Alright, so what I've done is I put x's at the 2 breakpoints. Alright, now again, there's another breakpoint out at negative infinity. Alright, now, if I look at my second step on here, it says mark each component of the magnitude individually. Okay? Because I have a pole at 0 frequency, right, this gets really, really tricky. What we know about a pole, right, if I go back and look at these things here, right, if I have a 0, I have a magnitude of 0 dB from an individual 0, and then I begin to rise after that 0. If I have a pole, I have a magnitude of 0 dB, and then I begin to fall 20 dB per decade after that pole. So if I have a pole at omega equal to 0, right, what I know is that I have been falling forever since omega equal to 0. And what I end up plotting for that guy is basically just a line that's falling, and he goes through the origin there on this graph. All right? Now this, what am I drawing right there? What I'm drawing is basically 20 log 10 of omega, negative 20 log 10 of omega. Remember what we end up doing, right, is we plug in j omegas here. So just to remind ourselves, what this becomes when I take 20 log 10 of the magnitude is it becomes 20 log 10 of 50, right, plus 20 log 10 of the magnitude of j omega over 5 plus 1 minus 20 log 10 of the magnitude of j omega. All right. You guys should recognize that this is just omega. Minus 20 log 10 of the magnitude of j omega over 100 plus 1. All right? So I want you guys to look at that. Basically what that's saying is if I want to plot the magnitude plot of this thing in dB, what I do is I plot the contribution from the constant plus the contribution from the 0 minus the contribution from this pole at 0 minus the contribution from this pole at 100. So what I can do is plot each one individually and then add them up. So I add this guy to this guy minus this guy minus this guy. Okay? So the part that I just added up was basically this. Okay? So this minus 20 log of omega is this guy. Right? I can see that if omega was equal to 1, right? If omega was equal to 1, this guy would be equal to 0, right? So let's just, I can try this right here. I can say, well, if omega equals 1, this guy is 0. If omega was equal to 0.1, I would have negative 20 log 10 of 0.1, which ends up being 20. And if I did omega equal to 10 to the minus 2, I'll end up seeing that this guy becomes plus 40. Okay? In other words, this guy's dropping very rapidly. Okay? Kind of makes sense, right? If omega was a really small number, right? 1 over a really small number becomes a really big number. So as the frequencies get smaller and smaller, this guy's getting bigger and bigger. Okay? Now, that's one component of this. Now I have to look at the 50. So I have to plot, according to this, 20 log of 50. Well, if I compute 20 log of 50, what I end up with is getting about 34. All right, so that's going to be, I don't know, sitting somewhere right around here. Okay. Like that. Now, what do I have to do? Well, I have to include the 0 and the pole, right? The 0 and the pole are relatively easy. I've marked the breakpoints, right? The first one here is a 0, so he is flat until I get to the 0, and then he rises up. And then I get a pole here, and he's going to fall down. Okay? Now what I have to do is at each individual frequency, what I have to do is I have to add all of these things up. Okay? I have to add all of these things up. Well, simplest thing, the way I look at this is at any given frequency, these guys all have to I have to sum them up. So in other words, right here, I'm saying I have 0 plus 0 plus 34 plus whatever this guy is. Okay? I think the easiest place for this to start is probably right here. According to this, at this particular frequency, I have a pole and a 0 each contributing 0 dB. I have this guy contributing 0 dB. And I have this guy contributing 34 dB. So what's going to happen is I am going to raise this up like so. In other words, I'm shifting this line up a little bit. All right. Now, it's going to continue that way until I get to the first breakpoint. Okay. So at the first breakpoint, first breakpoint is about here. Now I hit a 0, and so I'm going to level off. Oops, level off. And then here I hit a pole again, and I'm going to start to fall again at negative 20 dB per decade. Okay. So just to pay attention to what I did right there, what I can see is that at any given frequency, so let's say right here at omega equal to 1, what I've done is I've said, well, 1 0 and 1 pole both give me 0 dB. This guy is giving me a line that's falling. This guy is giving me a constant line at 34. So I basically add 34 to this line to shift this guy up. Then all I have to do is as frequency increases, and once I hit this 0, I bring in the effect of this 0, and once I come to this pole, I bring in the effect of that pole. Okay. So hopefully that helps. You want to look at more examples of that as you go through the week. Hopefully this example will help, but it follows that basic process that I showed you right here. Now, if I wanted to bring in the full curve, right? And one thing I should mention right quick is the full curve would look a little bit different, right? The full curve would be rounded here in these corners. All right. But if you follow this basic process, all right, you should be able to make good sense of what these things look like. Right. These ones are definitely harder where you have a pole or zero at the origin. But I think the basic idea you should be able to kind of make sense of.